containing a total of 4n plus 2 delocalized pi electrons. It should contain 4n plus 2 delocalized pi electrons. So if I substitute n is equal to 0, will I get that value? If I am substituting n is equal to 0, 4 into 0, 0. 0 plus 2 is what? 2, right? It was OH here. What will happen? This zinc will react with the oxygen here and form zinc oxide. The hydrogen will remain there, right? So what will happen? You will get C6H6, that is benzene. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry. So today we are back with session 7 of the chapter Hydrocarbons. So in the last session we discussed about aromatic hydrocarbons, right, and the nomenclature and the isomerism, and we discussed the structure of benzene, right, how it was developed, right, and we studied Kekulé structure as well as the resonance structures of benzene. Yes, resonance structure of benzene as well as the orbital structure of benzene. So we studied about the introduction about what is the exact structure of benzene, right. So in today's session we are going to study an important concept, that is aromaticity or aromatic character, which is governed based on a rule which is called as Haeckel's rule. Even this we are going to study. Then conditions for aromaticity. What are the conditions for this aromaticity? Then we'll study methods of preparation of benzene. So there are only few methods that we have to study here, as well as the physical properties of benzene we'll cover in this session. In the next session, we'll deal with the chemical properties of benzene. Alright, so let's begin with aromaticity or aromatic character. So we already know that what are we studying right now? It is about aromatic hydrocarbons, right? So how can you predict, or what are the conditions based on which you can say whether a compound is aromatic or not? Okay, so let's say benzene undergoes substitution reactions in spite of the high degree of unsaturation. This behavior is called as aromaticity or aromatic character. So even if it is having high level of unsaturation, still it prefers substitution reactions. So this is called as aromaticity or aromatic character. And of aromatic character of benzene can be explained on the basis of the compounds that follow the following features. Okay, so if a compound is having these features that we are going to discuss now, then we can say that this compound is aromatic. So let's see the resonance structure, the orbital structure, and the presence of 4n plus 2 pi electrons in the ring, where n is an integer, and this is called as the Haeckel's rule. So this is important. So let's understand in detail about this. Okay, so first let us understand what is Haeckel's rule, and then we'll move on to the conditions of aromaticity. So Haeckel's rule, or it is also called as the 4n plus 2 rule. Okay, so let's see. This rule states that the cyclic planar conjugated system, cyclic, it must be cyclic first of all, okay, that is ring structure, cyclic, we already know what is cyclic, right, and it must be planar, that means all the bonds are in the same plane, and then conjugated system means the double bonds which are present, like in the case of benzene, it must be alternatively present. That means if we are taking the example of benzene, we know that the double bonds are present alternatively, right? One double bond, then single bond, double bond, single bond, double bond, single bond. It's in that way, right? So that is called as conjugated system, containing a total of 4n plus 2 delocalized pi electrons. It should contain 4n plus 2 delocalized pi electrons, possess a high degree of unsaturation, and behave as an aromatic compound. And this N stands for 0, 1, 2, 3. All these values. It can't have any fractions or anything. Right. For example, let's take benzene. Benzene has 6 pi electrons due to 3 double bonds. Hence, benzene is aromatic compound. So, let's take the example of benzene, and how can you determine if this compound is aromatic based on Haeckel's rule. Let's see. So, in benzene, first what you have to see is how many double bonds are present, or how many pi electrons are present, we are going to see. Okay. So, you can see here 1, 2, 3. 3 pi bonds are present. If there are 3 pi bonds, that means how many pi electrons are present? Yes, 6 pi electrons are present, right? So, one bond is made up of 2 electrons, right? So, the number of bonds into 2 will give you the number of electrons. So, how many pi electrons are present in this system? There are 6 pi electrons, right? So what does the Huckel rule say? 4n plus 2 must be equal to 6 pi electrons. So how many electrons are there? That is what we are going to write here. So 4n plus 2 must give you 6. So now what we have to see, this n is here, right? This n. By substituting any values out of this, n is equal to 0, 1, 2, 3, etc. Are you able to get 6 value? So let's see if I am taking 4. So let's see here, if I am taking n value as 1. If I am taking n value is 1, what is 4 into 1 plus 2? 4 into 1 is 4, plus 2 is 6, right? So that means that it is following Huckel's rule. So if it is following Huckel's rule and if it is cyclic, planar and conjugated system, we can say the compound is aromatic. Same way, let's take the example of naphthalene. Naphthalene is 2 benzene combined together, right? Okay, so if you are considering naphthalene, total how many number of pi electrons are present? Yes, how many pi bonds are present? 1, 2, 3, 4, 5. Okay, and how many pi electrons are present? 5 into 2, 10, right? So that means 4n plus 2 must be equal to 10. 10 pi electrons. Total of 10 pi electrons must be there. So if I substitute what value for n, can I get 10? Is it possible? Let's see. If I am putting n is equal to 2, what happens? 4 into 2 plus 2. 4 into 2 is 8. 8 plus 2 is 10, right? So that means this is also following Huckel's rule. So as it is following Huckel's rule, it is cyclic, planar and conjugated system. We can say that naphthalene is also aromatic, right? Now let's consider another example here. Okay, so as you can see here, how many pi electrons are present here? There are only 1 pi. So for this example, how many pi electrons are present here? Or how many pi bonds are present here? Only 1, right? Only 1 pi bond is present. That means 2 pi electrons. So what does that mean? Again, so let's check Huckel's rule. 4n plus 2 will be equal to 2, right? In this case, 2 pi electrons are there. So 2. So if I substitute n is equal to 0, will I get that value? If I am substituting n is equal to 0, 4 into 0, 0. 0 plus 2 is what? 2, right? So again, it is following Huckel's rule. So this is how you have to calculate the aromaticity based on Huckel's rule. I hope that is clear. Now let us understand the conditions for aromaticity. The first thing is the molecule must be cyclic. Only the cyclic molecules will undergo aromaticity. Right, the molecules must be planar. We have already discussed this. And it must have a conjugated system of 4n plus 2 pi electrons. That means it must follow which rule? Huckel's rule. That is what we have just discussed now. It should follow Huckel's rule. That means 4n plus 2 pi electrons it must be containing. I hope this is clear. Right. So this is about aromaticity. Now moving on to the methods of preparation of benzene. So the first one is cyclic polymerization of ethyne. So we have already studied this under the chemical reactions of alkynes, right? So we have studied alkynes can undergo linear polymerization as well as cyclic polymerization. So when it undergoes 3 molecules of ethyne, when it undergoes cyclic polymerization, what is that you are getting? It is benzene, right? We have already studied this. So that was a chemical property of alkyne. Now it is a method of preparation of benzene, right? So you have to link in this way and study, so it will be easy for you. So cyclic polymerization of ethyne. When ethyne is passed over heated iron tube at 873 Kelvin, benzene is formed. So C2H2, right? So you have one ethyne here, second ethyne here, third molecule of ethyne here. So these 3 molecules of ethyne will undergo what polymerization? Cyclic polymerization when we are passing it over heated iron tube. So what is that you are going to get? C6H6. What is C6H6? We'll get benzene. Okay. So that is the first method of preparation. Second one is decarboxylation of aromatic acids. So we have already studied this part. What does decarboxylation means? D means, again, we have already discussed this. D means it's a removal of something. So decarboxylation means removal of CO2 is happening here from aromatic acids. Okay. So when sodium benzoate is heated with soda lime, decarboxylation takes place to form benzene. So we are taking sodium salt of the carboxylic acid, aromatic carboxylic acid. So as you can see here, we are starting off with sodium salt of benzoic acid. So this is your benzoic acid, COOH. Okay, now this hydrogen is being replaced by sodium. So you get sodium salt of benzoic acid. So what is that you can see here? The sodium salt of the benzoic acid we have taken here. Now what happens? We are reacting it with soda lime. That means sodium hydroxide and calcium oxide. It's a mixture of sodium hydroxide and calcium oxide. We have already discussed this. Now if we heat it, we'll get benzene. Okay, benzene is obtained. So we have studied it as decarboxylation, means we are going to remove carbon dioxide, right? So what happens here? The carbon dioxide, CO2, will be removed. Okay, and then you have one Na here, one more atom of sodium. That will combine, you'll get Na2. And you have one oxygen also here. So Na, 2 Na, that is Na2, and COO and one more O, it will be together Na2CO3, right? You will get Na2CO3. So this is how this reaction takes place, that is decarboxylation of sodium salt of aromatic acids, right? So the next method is reduction of phenol. Phenol is reduced to benzene by passing its vapors over heated zinc dust. Okay, so you already know what is phenol. On benzene you have OH group, which is an alcohol group, right? So it's called as phenol. When it reacts with zinc dust, what happens? You will get benzene and zinc oxide. Okay, so what is happening here? It was OH here. What will happen? This zinc will react with the oxygen here and form zinc oxide. The hydrogen will remain there, right? So what will happen? You will get C6H6, that is benzene. So I hope that is clear. We are reducing the phenol. That means we are adding hydrogen here. So I hope that is clear. Now moving on to the physical properties of benzene. So benzene is a colorless and volatile liquid. Its boiling point is 80 degrees Celsius and freezing point is 5.5 degrees Celsius. It has characteristic odor. It has a special smell. It has a characteristic smell by which we can determine it as benzene. Okay. Now it is a colorless and volatile liquid. It is highly inflammable and burns with sooty flame. Okay. Now it is lighter than water and its specific gravity at 20 degrees Celsius is 0.8788. Okay. Now it is immiscible with water. It is not miscible with water, but miscible with organic solvents such as alcohol and ether. So it's quite similar with alkanes, alkenes and alkynes, which are not generally soluble in water, but they are soluble in organic solvents, right? Benzene itself is a good solvent. Fat, resins, rubbers, etc. dissolve in it. And benzene also, when we were studying about alkanes, alkenes and alkynes, I hope you remember in that we have mentioned benzene as well. So it itself is a good solvent, right? Now it is a non-polar compound and its dipole moment is 0. Benzene is a non-polar compound and it is extremely poisonous substance. Inhalation of vapors or absorption through skin has a toxic effect. So benzene is actually carcinogenic, which we will be discussing in the last part of this chapter in the next upcoming sessions. So it is actually carcinogenic. It has toxic effects. It causes cancer. Okay. So these are all the physical properties of benzenes. In the next session, we'll be discussing about the chemical properties of benzene, by which we'll come to an end to this chapter. So I hope the topics we have discussed in this session is clear for you. So that's all for today. Thank you.